This video is all about bonding. Okay, so first, let's review some of the basic types of bonding. We have ionic, we have covalent, we have network covalent. Remember, ionic is when you have, amazingly enough, ions. You have something like Na plus being attracted to a Cl minus. You need two things for ionic bonding. You need ions, so a transfer of electrons to get ions, and then you have the electrostatic attraction between the ions, and that's what creates the bond. So remember, in ionic, you don't have like one molecule of NaCl. You have this whole network of ions that are all together, called a lattice. As opposed to covalent, which is, if you will remember, a sharing of electrons. So you have individual molecules. And then network covalent is actually a 3D, pardon the expression, network of covalent bonds that's very, very strong, like a diamond. Diamond is the hardest thing that we know of. And it's because there are a lot of bonds in all directions. I'll show you a model in class. That's the strongest there is. Now, as long as we're talking about bonding, I want to make a distinction between intermolecular bonds and intramolecular bonds. Intramolecular means bonds within the molecule. So, for example, water. Here's water. Intramolecular bonds are these guys, the OH bonds within the molecule. Once again, ionic doesn't really have this sort of thing. This is covalent we're talking about here. Intramolecular is these bonds between the molecule. Intermolecular are bonds between molecules. So if I have this water, let me change my color. I have water. Remember, in any kind of glass of water, I have a bazillion, uncountable number of water molecules. And they are, in fact, attracted to each other. And this attraction is an intermolecular bond. If I'm talking about boiling the water, for example, and making steam, those are the bonds that are going to break. It isn't these bonds, the intramolecular bonds, that are going to break when a phase change happens. It's the intermolecular bonds that break when a phase change happens. Now, there are different kinds of intermolecular bonds, but that's actually a story for another video. I just wanted to make you aware for the moment that there is such a thing. Now, we're going to focus on, in this video, is intramolecular bonds, bonds within the molecule. To do that, we're going to draw what they call Lewis-Dots structures. And we're going to stick with covalent Lewis-Dots structures, okay? So we're going to talk about covalent bonding here, strictly. Let's think about a periodic table. When we're talking about bonding, we are only talking about valence electrons. Valence electrons are the outermost S and P electrons. These don't count in valence at all. So the maximum number of valence electrons I could have for any given element is 8, because S is 2 and P is 6, so that's 8. Anything here in this first column, 1 valence. Anything here in this second column, 2 valence. 3, 4, 5, 6, 7, 8. We're not talking about transition metals at all. But even if we did, those guys would only have 2 valence electrons. It would be these S guys, because these don't count. They're inner shell. Okay, but since we're talking about covalent, we're only going to be talking about nonmetals bonding to nonmetals. So in order to draw a Lewis-Dots structure, the first thing we need to do is count all the valence electrons. Let's start with an easy molecule, CH4. So if I look here on my periodic table, here's carbon, it has 4 electrons, valence electrons. Here's hydrogen, it has 1 valence electron. So if my carbon has 4, and my hydrogen has 1, but I have 4 hydrogens. That gives me a total of 8 electrons to play with. Now, in a Lewis dot structure, dots represent valence electrons. And when they give you a formula like this, inevitably, almost inevitably, the first guy they write is the one that's in the center, and everything else is around it very symmetrically. It's not going to be a row, C to H to H to H to H, okay? It's not going to happen. This first guy's in the middle, everything else is around it. Now we distribute our electrons following, if we can, what's called the octet rule. The octet rule, octet meaning 8, right? The octet rule is give everybody 8. So I put 1 there, 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 1 there, 1 there, 1 there. Now remember, this is covalent, so they're sharing. These 8 go with carbon, but these 2 also go with this hydrogen, and those 2 with that hydrogen, and those 2 with that hydrogen, and those 2 with that hydrogen. Okay? So these circles here represent the shared electrons, right? So far, if I'm talking about Lewis dots, I've got a couple of rules. 1, count up all the valence electrons. Now, don't worry about where they came from. Which one were the carbon electrons? Which one were the hydrogen electrons? That won't get you very far. Just count them all up and put them in a big pile. Then you're going to make the skeletal structure. That is, figure out which element is in the middle and what elements are around it. Then you're going to distribute the electrons following the octet rule if possible. Now we can break the octet rule, but see if you can do it without breaking the octet rule first. Now some things will always break the octet rule. You've probably noticed hydrogen. Hydrogen always has 2 electrons, not 8. Because hydrogen only has S's. It has no p orbital. It has no place to put the 8 electrons. So hydrogen always has 2. Boron is actually another one that will break the octet rule. It's satisfied with 6 for reasons we don't need to go into. Boron's just weird. It's its own specialty of chemistry. Now, if you look at the periodic table, the octet rule comes about because 8 is a filled shell, right? 8 is where it's stable. 2 S's, 6 P's, stable. These guys here, carbon, nitrogen, oxygen, fluorine, neon, those guys are never going to break the octet rule ever. Carbon has always got 8 electrons. Nitrogen, always. Oxygen, always. Fluorine, always. Never break the octet rule. These below it, however, these nonmetals down here, they can break the octet rule if you need to. And the reason why they can is because they have d orbitals to put those extra electrons in. Even these guys do, because they just promote them up to the d's. But these guys never, because there is no extra d's to put any extra things in. Okay? Let me give you a few more rules that'll just make your life easy, or at least easier. So, always 4 bonds to carbon. That's one of the rules. Always 4 bonds to carbon. And you'll see that our structure here does have 4 bonds. One there, one there, one there, and one there. 4 bonds to carbon. I'll be adding to this, but let's draw another structure. Let's try NH3. And if you look at the periodic table, has 5 valence electrons. Once again, H has 1, and there's 3 of them. So once again, I have a total of 8 electrons. The N goes in the middle. H's are all around it. 1, 2, 3, 4, 5, 6, 7, 8. It does not matter which 3 sides of the N you put the H on. It doesn't matter at all. But you do need the H's on 3 sides and 1 side blank. So these electrons here, once again, that are between the N and the H, those are the bonding electrons. They are the ones being shared. Okay? Bonding electrons. This guy over here, those are non-bonding electrons. Non-bonding pairs. Okay? Non-bonding. So if we go back to our rules here, there are never non-bonding electrons on carbon. Nitrogen, on the other hand, usually is exactly what we just drew. 3 bonds and 1 lone pair. I can throw a few more of these at you. Halogens, fluorine, chlorine, bromine, iodine. Usually, I mean, these aren't hard and fast rules, but they're just here to give you an idea of what things look like. Halogens usually 1 bond and 3 lone pairs. And remember, lone pairs are these guys. This non-bonding pair is a lone pair. Now, all of these things are single bonds. Right? If I were to draw this with lines instead of dots, it would look like this. And those are single bonds. Perhaps you've heard of double bonds and triple bonds. Those things can happen too. Let's say I have carbon dioxide, CO2. Carbon is 4 valence electrons, oxygen is 6 valence electrons, and there's 2 of them. That's 12. 12 plus 4 is 16. My carbon's in the middle, and the only way this actually works out is to have double bonds. 2, 4, 6, 8, 10, 12, 14, 16. I have 16 electrons there. And you'll notice oxygen has 8, this oxygen has 8, this carbon has 8. I've done my rule here. My carbon has 4 bonds, but I'm sharing 4 pairs. Or 4 electrons rather, 2 pairs. That's a double bond. If I were to draw it with lines, it would look like that. Alright. Now, once I show people double bonds, suddenly everything's got a double bond. The only things that are allowed to be double bonds: carbon, nitrogen, oxygen, phosphorus, sulfur. Those are the only elements that have double or triple bonds, and only amongst each other. Okay? Halogens never have anything but single bonds. Okay? Never double or triple bonds. Okay? Only these guys and only with each other. Of course, a triple bond is something like HCN. H has 1, carbon has 4, nitrogen has 5, that adds up to 10, and it looks like this. That's a triple bond. Once again, though, my rules are being followed. Here's my carbon. It's still got 4 bonds. Here's my nitrogen, 3 bonds and 1 lone pair. I can make a rule with oxygen, too, by the way, that fits this guy, my carbon dioxide. Oxygen, usually, again, not hard and fast, but usually, 2 bonds and 2 lone pairs. Now, the other thing I need to tell you about Lewis dots is something called a resonance structure. resonance structures. The thing about Lewis dot theory, as a bonding theory, it's a quote-unquote simple theory. Not that it's easy, but that bonding is so complicated that this kind of relatively easy theory just doesn't cover it very well. Bonding's really hard. You want a hard bonding theory? No, never mind. You really don't want a hard bonding theory. Trust me. Lewis dot's a relatively simple theory. So, one structure sometimes doesn't cover it. So that's when you need something like resonance structures. Here's a classic example. CO3 2-. You'll recognize that as the polyatomic ion carbonate. Now, of course, that 2- means there's 2 extra electrons. So there's 4 valence electrons with carbon. There's 6 with oxygen. But there's 3 of them. And then there's 2 extra electrons. So that adds up to 24. Now, if you try to draw that, this CO3 2- structure, here's the carbon, there's 3 oxygens. Once again, it doesn't matter which 3 sides of the carbon you put those oxygens on. But you try to distribute so everybody's happy. The only way to do that, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Everybody's got 8. Everybody's happy. And that works. But there's nothing that makes this oxygen different from this one or this one. So this double bond here is just as likely to be on this oxygen or this oxygen as it is to this oxygen. So I have to draw all 3 structures. I have to draw the one where the double bond is on the top. And I have to draw the one where the double bond is on the right side. You'll notice they're the same in a lot of ways. I haven't moved my atoms around. I cannot do that. The only thing I've moved is the electrons. So usually you know there's a resonance structure when you've got a double bond that could equally be other places. Okay? That's a resonance. Basically the only way you learn Lewis dots is by doing them yourself. So we will be doing a lot of these drawing of structures in class. But that is the basic criteria for Lewis dot structures.